So is Earth going to look like a Death Star at a given instance? If you look at it from the outward perspective in like an isometric view?
Nah, it's not nearly as impressive. I guess the notional like laser Starshot laser array thing is about 1 kilometer across.
Okay.
So you know, a kilometer out of the disk of the Earth is super tiny. So yeah, not nearly that impressive.
That's a bummer.
Yeah, and it would get focused down to a spot.
Hello, space enthusiast. You're now listening to Space Forward Podcast. I'm Hussein Bukhari, your host. With me are Matthias Frenzel and Benjamin Shapiro. In this episode, we will explore the bleeding edge of satellite and satellite constellation miniaturization. These awe-inspiring crafts, commonly known as Chipsats, Wafersats, Sprites, Monarchs, Kicksats, Starchips, and even Smart Dust, are facilitating the rapid miniaturization of spacecraft, following an exponential trajectory stipulated by Moore's Law, and no doubt enabling new incredible possibilities and discoveries just around the corner. We talk about the unique physics and associated challenges that these low-mass vehicles face in space, how incredible engineering is overcoming them, and how Breakthrough Starshot project will tackle the very difficult problem of sending a spacecraft interstellar to Proxima b. Our guest today is Professor Zachary Manchester, who studied physics and aerospace engineering at Cornell University, earning his bachelor's and PhD respectively. Zach undertook his postdoc at Harvard and became assistant professor at Stanford University and later at Carnegie Mellon University, where he now heads the Robotic Exploration Lab. He received critical acclaim for his Kickstarter crowdfunded Kicksat project, deploying an armada of Chipsats in LEO, and has published together with Mason Peck and Avi Loeb, and is a member of the Breakthrough Starshot research team who are working on an interstellar spacecraft mission to Proxima b. During the recording of this session, we had some location-based background noise that you'll hear in this episode. We apologize for that. Zach, it's great to have you with us. You've studied physics, aerospace engineering, working under Professor Mason Peck in his Space Systems Design Studio at Cornell. And now you run quite the studio of your own, the Robotic Exploration Lab at Carnegie Mellon, designing, developing, leading multiple Chipsat projects and missions along the way. What drives you? What's been your motivation in all of this?
That's an interesting question. I guess, so I've been a space nerd since I was a little kid. I think as many of us can relate to. The Chipsat thing I latched onto as an undergrad when I first met Mason and heard about this stuff and just thought it was cool. You know, most of what I do is mostly, there's this combination of it's cool and fun and, you know, interesting. Doing these things is hard and ends up consuming a good chunk of your life, and you end up putting crazy hours into some of these projects and lots of frustration. And why do you do that, and why do you put yourself through that? I've kind of decided it's just there's this like kind of deep-seated notion somewhere that, you know, in my head that like I want the world to sort of be a little different than it is, and it should be a different way than it is.
So do you ever find yourself going back and forth between that ask? I mean, do you ever find that it's too much, or it's not enough, or it's not moving fast enough, and ask yourself questions like that?
It never moves fast enough, you know. That's always that's the problem. And there's just a certain point, there's just not enough hours, not enough money. Not enough, you know, that's just, it's always, there's like basically always too many cool things to do and not enough time and money to like feasibly do them all. That's like always how it is for me. So like I've gone through periods of my life where I've worked, you know, just like ungodly amounts and like to the point of like barely sleeping for like weeks around, like especially around when these satellite missions come together. It's just like absolute insanity. And what drives someone to do that? I don't know. It's just, you know, you just kind of like feel like this thing should exist and should be, you know, and it's cool. And it's, I don't know. At some point, there's just some weird like reptile brain thing that sort of gets at you. Cause I feel like, there's just like no, if you think about it from like a logical perspective or like you try to rationalize it, there's really no rationalizing some of these things. It's just kind of nuts. And the amount of like pain you're, and suffering you're willing to go through for some of these things seems completely nuts. There's a few quotes about this that I've heard too, about particularly about space stuff. That like I think I heard this from Tori Bruno of ULA. He said like I haven't heard anyone clearly articulate why we go to space. There's sort of no real explanation for this. He had some quote like that I liked, and I think it sort of gets at this. We all want to play with our toys, and we all want to do these things because it's cool. And at some level, it's sort of the same bug that led humanity to venture out to sea and stuff like this. And you just don't. There's just something in us that makes us want to do these things and go after the unknown and everything. And space is kind of that, where they just have to do it.
And it's interesting because, at some point we get an inspiration. So I'm curious to hear about your inspiration. What was it like to work with Professor Peck in the Space System Design Studio at Cornell? Was there a formative moment, your time, that brought you into spacecraft design and development?
Yeah, I don't know if it was like a single moment, but there was like a whole... So I got involved in that stuff, started working with Mason as a junior, as an undergraduate. And it was just like the coolest thing that I saw going on around me, in a research context on campus. And I just kind of latched onto it and thought it was awesome and ran with it. So it turned into like 10-year saga. But yeah, it was great. I don't think there was a single moment or anything like that. It was just sort of this thing that seemed really cool that it's also sort of like you end up kind of aligning with things that you're good at too, right?
Yeah, so you just took it on. And
so I just sort of naturally gravitated toward it,
So the topic here that we're trying to get a better understanding for our listeners, and our vision has always been to break it down to first principles. Femtosats, Attosats, Zeptosats, Yoctosats, commonly known as Chipsats. And there are so many other different names that you could sort of meander through. Can you give us an overview on what are Chipsats and other classes of really tiny spacecraft?
Yeah, so the naming system that involves sort of metric prefixes that you kind of just went through is completely confused and doesn't make any sense. And I think anyone who's seen it will tell you it doesn't make any sense. So let's sort of put those aside for a second. There's a few that make sense, right? That are sort of not trying to use those prefixes. So there's Cubesats, which have been around for, 20 years or so now, right? Which are these like 10 by 10 by 10 centimeter run kilogram-ish units of satellite. And those have kind of really totally blown up. And I think really it was a lack of a standard period more than necessarily a small sat thing. And what's happened, interestingly, in the last few years is it's blown up into larger and larger CubeSats. So now people are flying, 6Us and 12Us and things like this, right? So they've gotten bigger rather than smaller. And a lot of traditional aerospace, organizations have latched onto it just because it's a standard that enables them to like have an ICD and get a launch easily. So there's that. And that sort of started small and got bigger. And since then, there's been some interest in doing stuff still at the small scale. A couple of interesting efforts. So the Chipsat in particular that I've been involved with, and Mason and a few others, is at this. It's sort of an attempt at building things at the gram scale. So we're talking like gram-ish masses. The stuff that we've flown so far has been in the 3 to 4 gram range, pretty much, and like centimeter-ish size scale. So far, the things we've flown have been like, 3 to 4 centimeters, 3 to 4 grams, and the chip part kind of refers to them being flat rather than boxes or three-dimensional in some sense. And the chip part though is also it's in reference to the flat thing, but it also sort of is a little bit misleading, somewhat like those other names, in the sense that these are not in fact individual like microchips. That was a dream many years ago of several people in this area, but to date they've all kind of been basically little printed circuit boards, so just using off-the-shelf electronics, but the chip thing has sort of is, I think, nicely evocative of this idea of it's a small little rectangle of electronics and isn't like a box. So there's some other things floating around in there too. There's so I think now this original vision that dates back to like the early 90s at least of actual satellite on a chip where it is just the silicon wafer as the satellite. Now that's being referred to as a Wafersat. So there are people still talking about that. So I think that distinction is maybe somewhat clear. So you have Wafersat, Chipsat. And then in between Chipsats and Cubesats, there's also sort of now this growing ecosystem around what are called pocket cubes. So these kind of started out a little less than 10 years ago. Actually originated with Bob Twiggs, the originator of Cubesats, again, who kind of was like, oh, well, let's make a smaller cube. So these are basically, each dimension of the cube chopped in half. So they're 5 by 5 by 5 centimeters instead of 10 by 10 by 10. And there's a couple of companies who are doing interesting things with these now, and you can get rides for them. And they're kind of, there's something there. We'll see where it goes. It's a lot more challenging to do all the packaging than with standard CubeSats. And it's a lot harder to get batteries, unfortunately, than with standard CubeSats. So there's still sort of in this I think pocket cubes right now are roughly where CubeSats were, in the early 2000s, when they kind of just got started, where it was like a bunch of academics and hobbyists kind of playing around and trying to figure it out. But there's something cool there. And yeah, those are flying. Unfortunately, on the Chipsat side of things, we're not really flying anything due to a lot of regulatory hassles in getting permission to launch these things.
What is the biggest regulatory sort of role there at the moment? Is it the size? Is it impact? What's been holding you guys back?
The biggest thing is, so at the root of it, there's this notion that these things are small and therefore will be hard to track and see on radar. And therefore there's some concern over debris and tracking them and collision risk and this kind of thing. And I mean, the collision risk is, with any space object, is real, right? And we track objects down to the roughly 10 centimeter scale, 5 centimeter scale, down to the limits of the radars. And things move really fast in space, right? In low Earth orbit, things are moving 7 kilometers a second, and just, kinetic energy is mv squared. So there's a lot of kinetic energy there, even if the m is small, if the v is really big. So there is legitimate concern over even sort of gram scale things colliding with space assets. So that is a real risk. I don't want to downplay that. But what's happened, at least in the US, is that in order to get your spacecraft licensed, the sort of main thing that every spacecraft needs is a frequency allocation and a communications license. And so you can talk to your satellite, otherwise kind of what's the point? And so in the US, this happens via the FCC, Federal Communications Commission, and they've sort of unilaterally put themselves in charge of vetting space debris kind of issues, which is it's a weird thing for a communications organization to be making decisions based on space debris, which they really don't have expertise in-house and that kind of thing. So basically, right now, to get a license for any kind of satellite to fly as a U.S. flagged satellite out of the U.S., we have to get a license from the FCC, and they basically come down saying they won't license anything smaller than a 10 by 10 by 10 sort of CubeSat size, period, more or less. In fact, we tried recently to get pocket cubes licensed in the U.S. and weren't able to either. So they kind of have this blanket position that they won't license anything that's smaller than 10 centimeters in any dimension. So you have to sort of have something 10 centimeters sticking out in every direction in order for them to sort of give you a license. And we've had basically zero luck. Like I said, we tried pocket cubes as well and didn't really have any luck. And it's an unfortunate situation for us in the U.S. I think it's holding us back, at least I think part of this too is that there's not really big economic drivers to do this stuff at this point, right? So if Boeing and Lockheed were saying, oh, we need this, and pushed, I'm sure that they would relent and do it.
There's also the use case. If the use case was popular enough, I would imagine that would change the direction a little bit, because space industry is demand driven, as we know.
Yeah, I think that's a good point. Basically, I think if it's another side of the same. If there were economic interests in behind it, then things would likely change. But at the moment, it's both pocket cubes really and the Chipsat stuff that we do. They're sort of existing in this academic sort of researchy / hobbyist amateur radio kind of space where no one has any money and everyone's kind of doing it for fun. And therefore, the FCC looks at this and says, why should we take on any, risk for this? It doesn't look like it's got any sort of real benefit to.
So what's the magic? How are they useful? Like what is the most valuable use case in the scenario that CubeSats are not able to bring forth at the moment?
Yeah, so launching a CubeSat is still a order $100,000 undertaking, right? Like I've done it a few times now, and it's sort of, you can build the CubeSat for $10K, say. But all the testing most recently had to go through, if you don't have a connection to a test facility and you have to do it commercially, it can cost you $20,000 to do all the testing. So thermal vacuum, vibration, shock, all this stuff requires very specialized test facilities, and to get, it costs money, right? So even if I can build the satellite for under 10K, I'm talking at least double that to do a full batch of the testing that's required by launch providers. And then the launch. And, there's options for free launches, but if you have to pay full price commercially for a one-off at least, you're talking something, order 100K. So it's really hard to do a CubeSat, all in for under $100,000 still, I would say. So I think that's the sort of one big distinction, is that you're still talking about $100,000-ish to do anything with a CubeSat. And this is not even talking about labor costs and if you're a company, right? This is if you're a university, kind of situation. And maybe if you do them in bulk, right? Like if you're Planet Labs or one of these companies launching, dozens at a time, then amortize the per unit cost can go way down. But it's still, to do one, you're talking 100K. Maybe if you do a bunch, it's 20, 30K each. But now with and pocket cubes, by the way, are not that different. They're not you might think they'd be an order of magnitude different. They're maybe half because you still have to do all the testing, and the BOM cost for building a pocket cube is not much different from building a CubeSat. So maybe it's half the price, but I would probably contest that. So maybe you can build a pocket cube for a few $1,000. You still need to go through the $20,000 worth of testing, and the going price for those launches is $25K. 30K. So it's cheaper, but it's not an order of magnitude cheaper. All in, you might be talking half the price of a CubeSat. So 50K instead of 100K. So it's not a game changer. So the Chipsat, the main distinction here is these things are, they involve, maybe the single biggest distinction actually is that they involve zero touch labor. These things are printed circuit boards that just come off of a fab line ready to go, which is completely different from CubeSats and pocket cubes. In fact, pocket cubes might be harder to build than CubeSats because of... So these things involve, a structure that's got to be fabricated out of aluminum or 3D printer or whatever, and cabling and, wiring harness and solar panels, all this stuff that has to get integrated. And all of that, that's really the cost driver, right? I would argue. It's the labor of assembling that, it's the design work. And then the testing is largely based on mechanical failure of all these bits that are bolted together and, attached with whatever fasteners and epoxy and all this stuff. If you're talking about chipsats, there's just none of that. It doesn't exist. So the test, we still go through it because we have to, because these things ultimately get launched in some larger thing. But most of those test requirements are just, not relevant because it's a solid state, just, little tiny device that doesn't have any mechanical anything going on. And in fact, we've torture tested these things and dunked them in liquid nitrogen and had them running in ovens at several hundred degrees where the solder melts, and they still work. It's kind of insane how robust these solid state electronics are. So the testing gets easier. The fabrication issues go away completely because you're just send it to the board house and it comes back, and you can make them 100, 1,000, 10,000 at a time. And the prices get down to $dollars or $10, right? So there really is, more than just the size. I think the size is really not the big thing here. We could make, larger PCV satellites that would have kind of similar, things that might be on the order of 100 grams, and it'd be the same story. The fact that you don't have any assembly, any labor, and the thing's a solid state brick with no moving parts, no fasteners, right? This means that, these things are dramatically cheaper to build. They kind of scale like, consumer electronics in terms of pricing and fabrication. and they just don't. They're not susceptible to a lot of the failure modes, right?
So in terms of, and you mentioned two of these things that bring forth a fantastic idea for people who are in looking at it from an economical and business standpoint. It's versatile and it's low cost, but what are the applications?
Yeah, so the application end of it is the one I think that we kind of haven't figured out yet, and that's maybe the biggest challenge. So I think that there probably are Earth-facing applications of this kind of stuff that we kind of just haven't figured out yet. One nice one that probably could be done on like a PCB sat sort of scale is what is like really low data rate comms or
low range,
like LoRa stuff and like sort of along the lines of what Swarm is doing, if you're familiar with Swarm.
Yeah.
Their satellites are really just one PCB.
Correct.
Put in a small aluminum housing really for the battery.
Yeah.
So it's basically a single PCB. I think they might have a second one in there for solar for the other side, but it's basically just the only housing there and structures for the batteries, right? So that's close to being a single PCB satellite. And they, I think, had to go through a bunch of hassles on the regulatory side. To
currently going through them too.
Maybe still going through them.
Yeah.
So there's sort of like, I think there are Earth-facing things. They're probably in the realm of RF at low data rates where you just need lots of coverage, but you don't necessarily need high data rates. So you can use omnidirectional antennas and not need an attitude control system, things like this. So I think that there's probably some of that is, that exists. But the stuff that, obviously as a sort of long time space exploration kind of nerd, there are, I think, a lot of really compelling sort of planetary science exploration kind of things that we looked at in Mason's lab going back 10 years now, and that others have looked at, that we've had a few studies, some of them by other sort of co-conspirators from Mason's lab who are now out in the world. There's been some really cool things. So one that was looked at early on was kind of raining a bunch of these things down into an atmosphere. Either Earth or Mars or Venus, and putting them in basically, because they're essentially disposable and you can have lots of them, you can think about just kind of putting these things in harm's way in ways that you wouldn't risk your, $100 million or $1 billion primary spacecraft. So basically putting them into, on entry trajectories into planetary atmospheres and tracking them and maybe doing some in situ sensing is a reasonable thing to do. So you can imagine kind of getting into the interesting regions of the upper atmosphere around Earth in particular. This is interesting because it affects signal propagation for GPS and really all signals that go in and out of the atmosphere. And there's this region that's really hard to get to. It's sort of higher than balloons can fly, but lower than satellites can typically safely fly because they re-enter really fast. But maybe these things, we don't really care if they re-enter. So maybe we can eject a handful of these things, at regular intervals from a sort of higher orbiting mothership and let them re-enter and let them sort of explore this region of the atmosphere. Right now, the only way to get there is with sounding rockets. And that's sort of expensive and high latency, and you can't do it very frequently, right? But maybe this is another option for getting in there and getting at sort of some of these interesting problems in this region of the atmosphere that's sort of often nicknamed the ignorosphere. So there's that. Then there's you could think of doing similar things at Venus, which has a really interesting atmosphere that's currently, recently been a hot topic you probably heard about, right? With potential habitable regions in that atmosphere that are one atmosphere and like Earth-like, room temperature. Forget about the ammonia, but no big deal. And so you could think of doing things like this. So that's one application, is sort of entry probes. Another interesting one that's been looked at by a former colleague from Mason's lab, Justin Atchison, who's at Applied Physics Labs now, is studying asteroids with these kind of things. So it's a similar thing where you maybe wouldn't want to risk your $1 billion primary mission to go really close to the asteroid. But if you have 100 or 1,000 of these little tiny things that you don't necessarily care too much about crashing into the asteroid, maybe that's okay. And sort of the relevant comparison here is the way asteroid exploration is done now. The main issue is that we don't really know what these things look like before we get to them. And in particular, we don't know what their gravitational fields are like. So it's really hard to capture around them and approach them because you don't know what the dynamics are of your host spacecraft. So it's a really tricky control problem. And what ends up happening in practice now is we kind of very slowly approach them over months and try to estimate the gravity field of the asteroid as we get closer so that we know how to fly around it without crashing into it. And it's really, part of this is, it's really expensive to do this, and it means you can go study one asteroid over a couple of years. But you can imagine, doing some flyby maneuver where you release a whole bunch of chipsats and they kind of swarm around the asteroid and plow into it and you don't really care. And then you can maybe get a very quick snapshot of the gravity field and surface composition and take some pictures or whatever, and then relay that data back to the mothership satellite, and it can move along on its way and go study another asteroid. So there's sort of ideas like this too that have become kind of interesting.
So one of the things that I'm curious about, you brought up asteroids, deep space. One of the major problems is comms. So what kind of problems that chipsats will be able to solve when it comes to comms in regards to data transmission and the amount of data, and how will that work in deep space exploration?
So I think, all the things I mentioned kind of had this concept of a mothership that was sort of dropping these things off and also acting as a communication relay. And it's for exactly the reason you suggested. These things don't have propulsion or the ability to close a long-range comm link. So we've closed links to orbit with these things over like 1,000 or a couple thousand kilometers, and that's doable at modest data rates. But it's inverse square, right? So if you go twice as far, it's 4 times as bad. If you go 10 times as far, it's 100 times as bad in terms of the communication link. So it's a losing battle, and basically just because you're super power constrained on these things, it's sort of not really. You could do it theoretically with a ton of gain on the ground on the Earth with something like the Arecibo, may it rest in peace, or the square kilometer array. You could imagine, having a giant aperture with a lot of collecting area at the Earth, and then having the biggest receiver you could put together, and then getting, something like a bit or 2 per second out of something in deep space like this. But it's sort of right. It's sort of a losing battle, and you're not, because of the inverse square law kind of scaling of these things, right? You just need way more power on the transmit side than is really doable on these kind of small devices. So the sort of mothership / communication relay architecture, I think, is probably the way to go for anything beyond low Earth orbit. We can totally close link to these things in low Earth orbit, no problem, very easily. But I think in all these other contexts, the atmospheric entry probes, the sort of asteroid flyby kind of things, in those kind of scenarios where you're farther out, I think it makes a lot more sense to have a relay that's a larger spacecraft. That it's sort of the idea, right, that that the larger spacecraft can sort of stay at a safe standoff distance and communicate with these things and put these small disposable chipsat things in harm's way.
What are some of the other, in terms of the scope of the problems that we're going through right now, what are some of the other problems that satellites, such, the miniature size encounter that they're going through? How do these problems differ from their larger siblings?
Yeah, there's some interesting things that happen that might not be super intuitive if you at first glance. So one of them is that the scaling, as you get smaller, there's a bunch of things that scale differently that aren't, the scalings are not linear, right? So in particular, the way you collect power, right, is, solar, and this scales with surface area. But the amount of stuff you can cram into the spacecraft bus is really like a volume mass kind of thing. And that's scales with volume. So there's like an R squared versus R cubed kind of thing happening. And so a bunch of weird things happen because of this. It turns out as you get smaller, as a ratio of like how much power you can collect versus how much stuff you can fit inside, it actually, you get more power, you get more surface area per unit volume, right? But your energy storage goes down precipitously, right? So the amount of volume and or mass you can have for a battery gets really bad really fast, whereas the collection area for solar is kind of okay. versus what you can actually do or fit, right? So that's one of the reasons on the chipsets we don't have any energy storage. Basically, we have a few caps to do like buffering and whatever, but it's basically just right off the solar cells. So they really only function when they're in the sun, and they don't really work at all in eclipse. We can do things, really simple things, like we can charge up a cap enough to run a clock through eclipse. It's actually kind of incredible how low power real-time clock chips have gotten. Like talking, like tens or hundreds of nanowatts, you can run a clock. So you can run a clock for a long time off of a capacitor. So you can do things like that, right? Like ultra low power things that are just kind of saving state, like keeping a clock running or keeping something going in memory. But you can't really do any appreciable compute. Maybe there's ways of doing very tiny amounts on caps, but it gets really hard, right? So I would say like one of the biggest things is energy storage. There's just basically, as you get small, the mass and volume that you have to work with is just really small. Even if you can fit a battery somehow, there's current battery chemistries like the good batteries that use lithium. They suffer from like pretty restrictive thermal envelopes that they can work within, and they just permanently fail when they get like really, really cold in particular. And in eclipse on a really tiny thing, it's really hard to stay warm.
Correct.
So right now it's really hard to do batteries on these things. Pocket cubes are maybe, the smallest size where batteries are. Having recently tried to build one of those, it was quite challenging to get a battery to work on one of those things, and there aren't good options, and you end up with these kind of pouch cells, and then having to build some kind of like containment, thing to keep it from ballooning in vacuum, and you have to worry about thermal effects. So yeah, I would say energy storage is kind of the biggest, basic thing that you have to contend with on the small scale. And then everything else kind of scales with that. It's sort of like there's these kind of energy power considerations that really drive the whole thing. So the amount of instantaneous power you can get is totally then basically determined by solar and or capacitors for buffering small bursts of energy use.
So in regards to, you mentioned a little bit about the thermal, and I'm very curious about that. In regard the entire on a chipsat per se, the thermal management, are they in thermal equilibrium and in a constant state? How does that sort of play itself out?
Basically, they have such small thermal mass that they reach thermal equilibrium really, really fast. Right. So we've simulated this stuff a long time ago, and essentially what it looks like is the sort of temperature on these things looks like a square wave. Basically, you're in the sun, you're at some equilibrium temperature, you pass into eclipse, and it drops off a cliff, and then reaches thermal equilibrium at some really cold temperature, when you're in the dark. And then you come around on your orbit and pass back into the day side of the Earth, and it heats up again, really, really quickly. So it almost looks like a square wave, dark, light, just because there's nothing there, right? You're talking about a gram of mass, and so it's this scaling thing, right? You have kind of relatively a lot of surface area in relation to your mass compared to a larger spacecraft, like orders of magnitude different, actually, even than a CubeSat. So there's a ton of surface area. So there's a lot of area to collect heat from the sun and or expel heat in the dark. And there's just like almost no mass, relative to the amount of surface area. So all the heat's going to just, kind of leave instantaneously, more or less, when you're in the dark, and you're going to warm up really quickly when you're in the sun, and it just equilibrates super fast, just because there's no, like mass, right? In when you do thermodynamics, it sort of plays the same role as capacitance in electrical circuits, right? So there's just no capacitance.
Yeah,
you just charge up almost instantly and discharge almost instantly. So it's very square wavy.
Well, that's interesting. Now, another question that I'm sure our listeners are thinking about is attitude determination. How do you determine it? I'm very curious as to how that sort of plays out.
Yeah, so we don't, I guess, to date. The stuff that we've flown, and I don't think anyone's done really ADCS on this kind of size scale. It's kind of it's a fun open research question. It's something that I'm really interested in personally, because this is the kind of stuff I actually do. This is like where my academic cred, like what I actually do in my research lab, because we don't really do chipsats much these days because we can't fly them and there's no research funding for it. I'm actually a guidance, navigation, and control kind of person. This is like what my sort of actual say research chops are in. So we do control for all kinds of systems. And in particular, as a space guy, I'm particularly, I've just always loved the attitude control stuff, because it's actually really beautiful mathematically also. It's got this like group theory kind of flavor to it, right? The SO3, the rotation group. And so there's a bunch of fun math in there that I've always just thought was really pretty. So anyway, on the chipsat scale, we've never done it. We've looked into a bunch of things. I've got a bunch of crazy ideas, and other people have looked into different things you can do. The simplest thing you can do, which is what we actually intended to do on the first Kicksat mission, but did not, is to spin stabilize them. So this is like the most old school satellite attitude control technique there is. Back in the 60s, before computers were good and all this kind of stuff, the way you kept your satellite pointed, and in particular the way the first communication satellites that needed to point a dish at the ground worked, is you just took the whole satellite and spun it up like a top and relied on conservation of angular momentum to keep that angular momentum vector fixed in inertial space. So the whole satellite would just stay pointed. And this kind of evolved over the years to so-called dual spin spacecraft. So basically what you'd have is like this giant drum that was the main bus of the spacecraft would be spinning with this big angular momentum vector to keep the attitude sort of stabilized. And then there would be a despun platform. So it was actually a giant bearing with a bunch of like cable pass-throughs and this kind of stuff. And they would despin the end of the satellite with the big dish on it so that you could independently point the dish from the rest of the bus. So this is kind of how spacecraft attitude control worked way back in the day. And then it sort of maybe starting in the 80s, it became, when computers got better and you could actually run real-time control loops on these things, it became possible to fly what are called 3-axis stabilized spacecraft, where you use a feedback control system and actually sort of actively point the satellite. So with Kicksat, we initially intended we have an attitude control system in our kind of mothership spacecraft that did the deployment, and orient the mothership satellite towards the sun, such that the chipsats would come out with their solar cells pointing at the sun and spin the entire sort of mothership satellite up about that sun axis, and then deploy the chipsat so that they came out spinning and pointed with their solar cells pointed at the sun, and therefore would stay, because of conservation of angular momentum, again, they would stay pointed at the sun and stay sort of power positive in that sense. So that was kind of our initial intent and the initial solution to this attitude control problem. And it really kind of puts the burden on the larger spacecraft and relies on passive physics on the chipsat side of things. And this seemed like a pretty good idea. Ultimately, so I spent a decent amount of my PhD sort of figuring out how to do that. And it turned out there's some actually fun, there were some unsolved control problems in there on the mothership side of like, how do you spin this thing up? It turned out we needed to spin stabilize it about what's called a minor axis of inertia, which is in general with energy dissipation unstable. So we had to stabilize it about this unstable axis and do some fun things that kind of hadn't been done before. So I got some papers out of that and did a bunch of fun math. But yeah, so that's sort of one solution, right? Is this passive thing. Unfortunately, right now you can't reorient the chipsats. They're sort of stuck. But maybe that's okay for a lot of things, right? So in general, if these things are disposable and intended to work on the order of days or weeks, maybe that's okay. If they're a one-use kind of thing, maybe you kind of pick an attitude and spin them up and let them go, and they'll just stay pointed, and that's okay. But if you want them to have sort of multi-use or the ability to reorient, now it's a much harder problem. So we've looked into this a bit. We have, in the last year or so in my lab, we did this paper that the paper was all about kind of Cubesats and or pocket cubes, so a little bit larger into the scale, but the kind of, secret intent was to, really be able to do this kind of stuff on chipsats or very small things. So the classical kind of way you actuate a spacecraft is with reaction wheels, so there's flywheels, right? So you spin the flywheel one way, and because of conservation of angular momentum, the body of the spacecraft will spin the other way. So those are irritating to deal with. They're okay on larger spacecraft, but sort of these scaling arguments, as with everything else, they don't scale down well. So you think about having like a motor with bearings and a flywheel, and you need 3 of them for roll, pitch, and yaw. So doing something like that on a sort of very small scale, and talking about all this sort of solid state fabrication we talked about before being really nice, that all goes away when you need spinning parts and motors and bearings and lubrication for the bearings, right? So all this is bad, and this gets you back into the realm of needing exquisite labor and testing and all this kind of stuff. Even lubricating bearings in space is a whole research field unto itself. It's really, really terrible to have grease and lubrication that works for a long period of time in space. So at any rate, so we don't like those things, and we don't really want them on chipsats. And they're also they're not planar, right? They kind of like, whatever you do there is going to have to stick off the board and be weird. So there's another way to actuate spacecraft that's been used forever, which are magnetic torque coils. So these are basically electromagnets. It's a big wire coil you have on a satellite. You run current through it, it generates a magnetic moment, and now this magnetic moment interacts with the Earth's magnetic field to produce a torque. So it's exactly the same effect that makes your compass needle point north. So you can think of this as like turning the whole spacecraft into a giant compass needle and getting the Earth's magnetic field to kind of tug on it and torque it around. So this has been around forever. In fact, goes back to the 60s, back to the sort of birth of astronautics. And the problem with it is that interaction with the Earth's magnetic field, there's sort of a cross-product interaction between the magnetic moment you generate on the spacecraft and the magnetic field vector of the Earth. And that cross-product thing, right, you remember your right-hand rule from, freshman physics or whatever. What ends up happening is the torque, you get the torque from this cross-product interaction, and it's such that you can't ever produce a torque parallel to the B vector, to the magnetic field vector of the Earth. So you only can ever get torque in 2 degrees of freedom in sort of this plane perpendicular to the local magnetic field vector. So this is, in robotics, this is what we call underactuation. It's an underactuated system. We don't have full control of all our degrees of freedom instantaneously. So if that were the end of the story, if the B vector was just what it is, you'd be kind of out of luck, and you wouldn't be able to actually fully control your satellite. You'd never be able to rotate it or cancel out disturbances in this direction parallel to the B vector. Thankfully, though, satellites are moving around in orbit around the Earth, and the Earth's magnetic field is not uniform. It's actually quite nasty and crazy looking at a fine scale. So that means the B vector is changing as you move around. So the idea we had was, the magnetic field is much more complicated, and we know what it looks like. We have good maps of it. And it's not a terrible assumption to say you know where you are on board the satellite. So you could do this with GPS or whatever. We could tell the satellite, right, upload its orbit. And so it knows. And so what you can do there then is say, okay, the B vector is here right now, so I can't get torque in this direction right now, but in 5 minutes it'll be over here in this other direction. So if I'm a little bit clever and I have a map of the magnetic field and I know my orbit, I can plan a longer maneuver that might take 4 or 5 minutes that kind of takes advantage of where the B vector is going to be in the future in order to control my attitude and get me where I need to be in my full kind of 3 degree of freedom pitch, roll, yaw. So that's kind of the core of the idea. And basically we developed an algorithm that can do this. So given a map and given an orbit, it can look ahead and figure out what it needs to do over the next few minutes to achieve a desired pointing state. So this is cool because now it's just these magnetic torque coils, which are just wire coils. And these can be made in a board and all that kind of stuff in their solid state. So that's the other idea.
I want to continue this conversation, but I want to move in a separate direction because you said now you're focused on control mostly. But let's talk about it from a different scale or at a different scale. Constellation management. One of the key primers that is unfolding itself in this industry. Tell us a little bit about your work on the bio-inspired position control of spacecraft.
I had a master's student who's since gone to work at SpaceX, who's into this kind of stuff, who we kind of looked at a bit. So the sort of bio-inspired thing is just the sort of like these deployable boom actuator ideas that you're referring to. Yeah. So this is another actuation idea. So the torque coils, right, are nice because they're solid state. But they have this limitation of, it might take 5 minutes to get where you need to be.
Fair.
And you don't have full 3-axis control. So another idea that I like, that we played around with, that we've submitted a proposal on, So I'm fingers crossed this is going to come through in the next couple of months, and we'll get to work on this. And one of my current grad students is really into this idea. And it also has sort of other applications aside from chipsats. But my original sort of, spark for this idea was the chipsat stuff. So this idea is, we talked about the flywheel idea, these kind of momentum control devices, flywheel, actuators, reaction wheels, whatever you call them. So these things traditionally, right, they're these flywheels tucked away inside the spacecraft. And this whole scaling thing we talked about, as you get small, this kind of doesn't work and gets bad for you. So one of the things that happens is that as you get small in particular, these wheels spin really fast to actuate the host spacecraft, and even just to stabilize and point. They might be spinning at hundreds of hertz, pretty fast. And what that does is produce vibration. So you can imagine these wheels, you balance them really well, but there's always little tiny bits of imbalance. So if this thing's spinning around, a couple hundred times a second, you're getting like 200 hertz vibrations just shaking you. Think about a washing machine, where the clothes are a little off in the drum and this thing's spinning around. That's what's happening with these reaction wheels. And you can make it really well balanced, but never, achieve perfection. So this is always there. This is particularly bad on space telescopes. On large space telescopes, you want to do long exposures with these things, right? You want to stare, you're trying to image exoplanets. You want to do like minutes long exposures because these are really dim objects. So you need to stare super stably for minutes. And if you have these things doing the washing machine thing to you over that, it's going to blur your image, right? So this happens now. And this is actually one of the big things limiting the ability to do astronomy on smaller satellites, on Cubesats in particular. On bigger spacecraft, we can do all kinds of vibration isolation and damping around the wheels to try to isolate them from the rest of the spacecraft structure and keep these vibrations from propagating into the optics and all this stuff. And this is what's done on Hubble and James Webb, right? They do really big things with really kind of crazy isolation strategies to keep the wheels from shaking the rest of the satellite. You can't do it on a CubeSat, right? The wheels, first of all, the wheels take up more volume as a fraction of the spacecraft because of these scaling issues, and you just don't have the mass budget to have all kinds of damping and isolation stuff baked in to keep these things from shaking the rest of the satellite. So you really want to get rid of that. Okay, so here's the key idea with this kind of crazy bio-inspired thing. The inspiration is from things like falling cats and in particular geckos. It turns out geckos are super, super good at attitude control. They can they can fall off a tree, and they actually can do, and there's these flying geckos too. They're really cool. They can actually do 3 off complete pitch roll yaw attitude control extremely well by wiggling their tails around. And it's sort of intuitive. You can imagine how this works, right? You kind of whip the tail around, and there's good videos. Some biomechanics folks about 5-6 years ago did a series of experiments on geckos to try to get at this. They had them stand upside down on a metal plate. So, geckos can stand, they have these kind of magic Van der Waals feet, and they can walk up walls and all this stuff. So they put the geckos on these plates, and then they gave them a little zap. They ran electricity through the plate to zap them to cause them to fall off. And they kind of universally, without fail, they'll right themselves and end up on their feet, no matter what. It's pretty incredible. And these geckos are 3-4 centimeters long and weigh a few grams. So they're at this chipsat size scale. So this clearly works. And the main magical thing here versus the flywheel is this tail is it's extending out from the body. So the idea here is we should put tails on our satellites. We should have these call them booms or arms or tails that extend out from the body that have, say, a mass on the tip of the boom. And what this gets you is inertia. There's a quadratic scaling here. This nonlinear scaling thing keeps coming up, right, as you get small. So this is the inertia of this boom or the wheel. It goes with mass times length squared. So you get a squared advantage by making the thing longer. So you think about a tiny little wheel inside the spacecraft versus you take the same amount of mass and stick it out on a boom. You get this length squared advantage. So it's a huge win, even if it's the same mass. And what this lets you do is now, instead of having to spin this little wheel at hundreds of hertz, you can have this boom hanging out here that can move super, super slow. Fraction of a hertz, millihertz, right? It just needs to move fast enough to reorient the bus and potentially cancel out external disturbances from solar pressure and drag. So this not only gets you, if you have 3 booms, you can now do pitch roll yaw, but also you can do extremely stable long-term pointing without any vibration now. So this enables the long exposure astronomy kind of stuff on a small spacecraft. So that's kind of the magic, is that this length squared thing lets you move slow. and lets you kind of stare without having any shaking.
It's very interesting that you brought this up. Now, my question to you is that been presented, simulated, can it actually work? And are there potential tech demos that should be conducted on this in order to make it into a reality?
Definitely. So we have, like I said, we have a proposal into NASA, myself and a few collaborators. Actually, we have a couple of astronomers on board who are into trying to do astronomy on small satellites, who are experts at the optics and all this kind of stuff, right? Who've actually simulated that side of the problem. So my group is good at the control stuff, and we have mechanical people who think about how to build the thing and then how to actually do the control. And we've said, if we can build this and we have these specs on the optics and the sensors, we can achieve this level of pointing. And we've simulated all that with all the noise and Monte Carlo with all the environmental disturbances. So so we have that, and then we actually partnered with a few different astronomy folks who are experts at building these small telescopes and the CCDs and the sensors and all this other stuff, who can tell us the noise specs, and they're interested in actually building it. So we have actually, hopefully, fingers crossed, this gets funded by NASA Astrophysics in the next, and we get a couple of years to actually. The plan is to actually build a lab demo of this, where we get the real sensors, we build the actuators, and we do it in 1 degree of freedom or maybe 2 degrees of freedom in the lab, and show that we can, with reasonable disturbances, actually point to this level of ultra high precision. So that's the next 2 years. If it gets funded, we're going to do it in the lab and show that it should be possible, and with real hardware, and run the control loops and all that stuff. And then the follow-on from there, if it works in the lab, would be to do a flight demo.
Yeah.
So this may be 3 to 5 years out. Fingers crossed if everything goes well and we get money to do it, and NASA thinks it's worth doing. So
I mean, again, like with anything else, it takes time, cash, patience at most times. You got to sit back and let the show be on the road. Now, does this relate back to Chipsats?
Yeah, so the original idea here, so it has application to these larger, still very small by traditional standards, trying to do, high quality astronomy on like something like a 3U Cubesat, right? With sub-arc second pointing is really hard. But the Chipsat idea is that, so we talked about this magnetic torque coil thing. That does scale to the Chipsat, but you could also imagine having something like these little booms, little tails on the Chipsats sticking out that can then do 3-axis, real-time pointing. So the torquer thing, that's maybe good to 5 or 10 degrees, and it's slow. It takes like 4 or 5 minutes to reorient. The boom thing is instant, right? You have actually 3-DOF control. You could point right now, and you could do sort of sub-degree level pointing, like accurate pointing, like what you would think of as attitude control on a traditional spacecraft with wheels. And that, right, it's going back to that length squared scaling argument. It's something we could actually build at this centimeter scale. And the nature sort of showed us, geckos are literally the same size as the Chipsats, right, that we talked about. They're like 3-4 grams and 3-4 centimeters. So it's at the right scale, and it works, right? So you could imagine if you could build some little, like, say, piezo actuated 1-DOF booms, things like this, on these Chipsats, that you could do full 3-axis pointing.
Full 3-axis pointing.
Fine pointing.
And that'll help resolve a lot of the other problems. Now, we found in the preparation for the recording, I was reading a paper by the Initiative for Interstellar Studies that talks about integrating circuits to size of 1 centimeter and even smaller. They're calling it smart dust. Why do we need smaller satellites? What could we do with them, and how could we go about creating them?
Technically, it's within our means to build these kind of centimeter scale devices. On the semiconductor end of things, like, you can build these things. It's been possible to build these things for a decade, at least, right? It's basically at this point, it would be a custom IC that, like, any fabless there's hundreds of fabless semiconductor companies around the world who do this, right? Where you design an IC and then you go send it out to a foundry and they make you however many, right? This is like what ARM does. So this is possible. And so you could stick, a microcontroller and whatever kind of power regulator and all the bits and pieces that you would want, and a radio, right? you could stick all that on a single chip, and then probably, the solar cells are different. They live in different processes, technologies and stuff, but you can do these sort of multi-chip module packaging techniques where they basically bond the wafers back to back. So you could imagine, you could definitely integrate sort of solar and the rest of the smarts on a single chip that would be like a square centimeter or something. This is totally within, modern technology to do. It's a few $1 million to do. It's the problem, right?
Yeah.
Just because of how that stuff works, and how much it costs to do a single fab run. But we could totally do it. So if someone like DARPA wanted chipsets, and if they were willing to throw $10 million at it over a couple of years, you could have them. So this is not hard, in some sense. It's a problem of time and money. As far as why, I think there's all the reasons we kind of talked about, around, there's probably some commercial Earth-facing applications, low data rate comms where you want lots of coverage. There's lots of space exploration applications. There's also, you don't have to think too hard to imagine DoD-flavored applications for really small things that can't be tracked, right? It sort of turns the curse we have been dealing with regard to trackability and debris concerns, to try to get licensed. Well, if they really are untrackable at this 1 centimeter scale, say, then maybe there's some people who view that as a pro, not a con. So you can imagine that there's other things you might want to do.
So I'm trying to maneuver the conversation in a point where, we get to that deep space aspect. So our MO at Space Forward is to dissect humanity's push towards becoming an interplanetary species and have a multiplanetary existence. We have strategically tried to break it down into actionable steps. And what you're doing with Team Breakthrough initiatives is something that you're already ahead of us in one step there. But could you share a bit about Breakthrough Star Project and how you got involved?
Yeah. Breakthrough Starshot is a very cool thing. So for those who don't know, it's this sort of initiative, project, whatever you call it, started by Yuri Milner in, I want to say, 2017. The idea being to sort of actually put a real investment and then get real smart people looking hard at the most practical means of building an interstellar spacecraft possible. So to try to actually get serious about building an interstellar mission, and so to send a spacecraft outside the solar system to our nearest neighboring other solar systems, right? Probably Alpha Centauri, which is kind of 4 light years away. So that's really hard. And Starshot so I got involved in that pretty much right from the beginning, so a bunch of my PhD work was done at NASA Ames. And at the time, the center director was a guy named Pete Warden, who's an awesome guy with basically a long history of doing just about every cool thing you've heard about in space over the last, 20 or 30 years. He's had some hand in. So he's the sort of chairman of the Breakthrough effort. And he sort of, retired from NASA and then went to run Starshot more or less. And I was at Ames while he was center director, and he was a very big proponent of all the Chipsat stuff. And the notional plan with Starshot is to build a sort of gram scale spacecraft Chipsat, and sort of attach it to some kind of light sail, think solar sail, maybe a few meters across, and then to accelerate that light sail with a big laser, with a big ground-based laser on Earth. So you would launch this thing into low Earth orbit, say, and then have a giant laser on the ground, shoot at it with, many, many thousands of suns worth of power, and accelerate it really fast to some, say 20% the speed of light kind of speed, so that it could reach Alpha Centauri in, say, 20 years. So that's kind of the overall idea. And a big part of this is getting sort of a gram scale spacecraft onto a light sail. So that's sort of how I got involved. Pete Warden sort of, roped me in early on because of the Chipsat stuff. And so there's some obvious connections. And they were very supportive of the Kicksat work. I mean, Pete was when I was at Ames for sure. That's where I did all the original Kicksat work. And then post Ames, Kicksat 2, Breakthrough helped out a ton with sort of basically supporting me while I was doing that stuff on the weekends, so that I could keep doing it in my spare time when I wasn't getting paid to do it.
So with the Breakthrough Starshot project, what is the payload on that? Is it a camera? Is it?
Yeah, so I think notionally there's some sort of camera and some set of science sensors, and the idea is that you would do a flyby of Proxima b, this planet that's maybe in the habitable zone, and image it and take some measurements, whatever you can do in a gram, and somehow transmit the pictures and data back to Earth. So this is kind of the notional idea. You would do a flyby, take some pictures, and transmit them back. As far as how all that works and what that looks like, no one really knows. There's certain parts of the project that are surprisingly doable and near term.
Yeah.
In particular, the solar sail seems quite doable.
Yeah.
There's Harry Atwater at Caltech, who's an expert in metamaterials, has come on board the project, and his lab has done some really amazing work in the last few years. And basically, it looks like we can build sort of ultra thin, ultra low absorptivity, super shiny materials that sort of work in this context, that would be thin and light enough and reflective enough, and not cook under a big laser beam. So it looks like they can build these things. They basically can build them now, but they can only build little pieces of them sort of centimeters across. And so now it's basically a manufacturing problem of how do we go from something in the lab this big to something that's a couple meters across and maintain tight process control so there's no defects at that size scale. So that seems actually quite tractable. Like maybe in 5 years you could build the sail for this thing.
Yeah.
I think the chipsat side of it is also quite doable. From my perspective, it's like, we can build electronics, on thin films. We can build, these things like we just talked about the chipsats. And if you had, say $10 million to throw at this, you could get a fabless semiconductor shop to design you a thing, and you could go get it fab. There's, I think, integration challenges of like, okay, so probably if I had to do this now, I would go design something that had a bunch of stuff on it and try to thin the wafer down and then somehow bound it to the sail. How all that works is a question mark. But in principle, you can build the chip stuff with like IMUs and computers and all kinds of sensors. You can even do cameras on thin film devices. So like a bunch of that's like sensing and control and compute is all possible. So the parts of this that are really hard and unsolved, one that immediately comes up when you start talking about the chipsat is communication back to Earth over these extreme distance scales.
Correct.
In this extremely small size scale. So it's not as hopeless as you might think either. If you had a big spacecraft, you could do it, it turns out. So in particular, the people are currently looking at optical communications for this. So laser comm, which has already been done on conventional spacecraft from the moon.
Yeah.
And people have achieved, record data rates at the moon a few years ago. And currently there's a bunch of satellites doing laser comm from low Earth orbit.
Correct. It's
been an active research area for small sats for the last 5-ish years and has been done in deep space already. So it turns out, theoretically, if you work out the sort of link budget calculations, if you had something like a conventional spacecraft at Alpha Centauri with like a 20 watt, 50 watt laser transmitter, and then something on the ground akin to like a current 30 meter class telescope used for astronomy, you can close a comms link like reasonably well. Like it actually works, and you can achieve like modest data rates. It's like not too terrible.
Yeah.
The problem is we can't have the 50 watt laser transmitter on the gram scale spacecraft, right? So that's actually what the hard part is. It's like trying to figure out, okay, if we had this like, beefy laser transmitter, sort of similar to the thing that flew around the moon a few years ago and demoed that, and like the biggest optical telescope on the ground we could find, you could do it. But now we have to figure out how to fit that on a chipsat. So that's super hard. No one really knows how that's going to shape up or look, right? And you have the power limitation and all these other problems. So that's really hard.
Yeah.
But that's sort of this is like a integration challenge, I guess, and a power challenge. And there's probably some ways to do it, although the data rates will probably be really, really low. So now you're talking about, oh, well, how do we send images? No one knows. So that's, that's hard, but probably doable in and also I should mention the notional timeline for all of this is like decades. It's like a 20 to 30 year project notionally, right? So you can imagine, if we can do that now in a box this big with 50 watts, maybe in 30 years we can do it in a chip this big.
That big.
If you imagine the way these things scale, and there's exponential scaling with laser technology, sort of like Moore's law, that's been happening for a while. Okay, so that's one laser problem. The other obvious laser problem here is this ground-based giant laser that's going to sort of shoot the light sail and accelerate it. That's the other really hard thing. There's also really fantastic laser experts involved in Starshot looking at that problem. And there's been actually in the last year and a half or so, there's been some really, really encouraging work done by a handful of groups looking at building, essentially the way to do this, right, is not to build one giant laser. It's to sort of phase together a ton of small, reasonable lasers. And make a giant array of them. The hard part is you have to build what's called a phased array. They have to all be kind of synchronized and phase locked so that they add constructively. And we do this in radio all the time. This is how all modern radars work. And in fact, people have done this in optical as well, in lab sort of benchtop experiments and things like this. And there's been some DoD funded work on this in the last decade or so for maybe less benign purposes. But you can phase, so people have phased order 20 lasers together and to make a high power beam. The problem is for the Starshot thing, we probably need order, I don't know, 100,000 or to 1 million or something like this, like a crazy number of lasers, all phased together, and they have to all line up at this target really far away through the atmosphere. So going back to this whole thing about the atmosphere and how it messes with radio propagation, obviously it also messes with light in the same way. And this is why stars twinkle and all this stuff. So getting the laser to stay focused after passing through the atmosphere is super, super hard. And so there's this whole field called adaptive optics that, in astronomy, people have been looking at this the other direction to try to focus light from stars on telescopes on the ground. And so there's a bunch of work that's gone on that side of things, how to correct the atmospheric disturbances. And there's new work going on in phasing a whole bunch of lasers together. But yeah, it's really this question of massive scaling up of a bunch of things where there's hints today that, pieces of this have worked at small scales in the lab. And we need to sort of scale a bunch of it up by a few orders of magnitude. And so that's kind of where I would say roughly where that stuff is at. I would say that the hard parts are comms over 4 light years and giant laser array with more elements that need to get phased together than has ever been done by a couple orders of magnitude.
So is Earth going to look like a Death Star at a given instance if you look at it from the outward perspective in an isometric view?
Nah, it's not nearly as impressive. I guess the notional laser Starshot laser array thing is about 1 kilometer across.
Okay.
So a kilometer out of the disk of the Earth is super tiny. So yeah, not nearly that impressive.
That's a bummer.
Yeah. And it would get focused down to a spot, right? So we want to focus this down to some sail thing that's maybe a couple meters across. Yeah. So it's ultimately out in space. It's going to be a spot of 2 meters across or something like this.
But could you do it? Could you have a sail that could be potentially in maybe a geo orbit that's sort of in one place that the laser points at?
Yeah, I think in principle. So the idea is to launch this thing into some sort of Earth orbit, maybe a Molniya orbit. I don't know, something where it has a good amount of hang time over this laser, and then basically shoot at it over the span of a couple minutes. So the entire acceleration phase might be is notionally something like 2 minutes, where the beam would be on and the thing would be accelerating.
So the problem here is fast, but also efficient. What about the notional ideas that are being thrown around nuclear propulsion, the potential capabilities? I mean, it's not necessarily small, but that's another problem that you dive into. But what are some hesitancies around tackling that on board this project.
So there's really no like nuclear anything in the Starshot project. I mean, I think that's a fascinating topic to talk about as a separate thing. So maybe there is something like that, like a small radioisotope power source on something like Starshot. As far as propulsion goes, this is a topic with a long history and a bunch of like really successful and really awesome looking work that's, you know, stuff we could build now that arguably we could have built 20, 30 years ago if we wanted to. But there's sort of this, you know, stigma attached to things nuclear. And there's, in some cases, like very real, scary prospects for nuclear proliferation along with these things, right? So the main sort of ways to build a nuclear rocket, there's a couple. One is a so-called nuclear thermal rocket, where you just take some fluid and superheat it, and turn it into like really high pressure steam, essentially, by running it through a reactor core. So this idea has been built several times and demonstrated very successfwere In fact, there were plans to build. There was a project called NERVA back in the 60s that built nuclear thermal rockets, and there were designs for a nuclear powered successor to the Saturn V that flew us to the moon. Right. So the idea was that if you built a nuclear thermal version of the Saturn V, the ISP, which is like rocket speak for gas mileage, can be right out the gate about double for a nuclear thermal rocket compared to conventional chemical rocket. So it gets you a lot more bang for your buck. So roughly, you can think of it as like twice the gas mileage. So this is good, and this is something that again, there's NERVA program back in the day. They built these things, they test fired them a whole bunch. They work. If we wanted to build these things, we could have built them in the 70s. But there's lots of safety issues with these things. There were studies done back in the day of, rockets occasionally blow up and crash. What happens if your nuclear thermal rocket blows up on the pad? Or sort of something bad happens, shortly afterwards and it crashes in the ocean, or God forbid crashes on a populated area, right? So there's all these things that could go badly there. And you can easily imagine scenarios where very bad things could happen. So that's one option, is this nuclear thermal rocket. And I think it's certainly it should be seen as like a factor of 2 kind of improvement over chemical rockets that we built and fly now. It's sort of not, it would be awesome to have, but it's not this sort of like several order of magnitude game changer, fly us, around the solar system in a day, fly us to Alpha Centauri kind of thing. It's sort of like a factor of a couple improvement on current chemical rockets. The other main idea for nuclear propulsion is this like Project Orion idea, for those who've heard of this. And there's an awesome book called Project Orion on this that you can read about. This was another sort of child of the 60s kind of idea that unfortunately, did not come to pass, or fortunately, depending on your views. But the idea here is basically you can build a really, really large spacecraft with essentially like a giant suspension system at the rear end and shoot nuclear bombs out the back and just blow them up at, I don't know, a couple hertz. So you're kind of blowing up nuclear bombs once every second or two or something like this. And you have this giant sort of like steel pusher plate at the back that's absorbing that impact through some kind of big suspension system to kind of smooth out those giant transients, so that the crew doesn't, get jolted to death or whatever during this process. So this actually works too. Prototypes of this were built that used conventional explosives, and they actually flew them. So they sort of solved a bunch of the stability issues and dynamics issues, and built these things. So the basic idea of blowing bombs up behind your rocket to make it go, and having this kind of suspension system to smooth that out, that all works, and that was all built. The nuclear aspect of it also works, it turns out. As part of this program, briefcase-sized nuclear bombs were developed to make this work. But then sort of, this was in the late 60s, I guess, and the prospect of briefcase-sized nuclear bombs was extremely scary for a whole bunch of reasons. Nuclear proliferation, possibly setting these things off in populated cities and things. So basically no one wanted to have, briefcase-sized nuclear bombs out in the wild. And there was this huge concern that if they were really developed as part of this program, bad things would happen, and these would get out somehow and lead to some really terrible things. So that's sort of, I would say those are the two ways to do it. And Project Orion, there were these amazing visions of like being able to fly around the solar system and having these giant spacecraft that were like, cruise ships with huge living space and the ability to kind of like fly these things around and fly to Mars in a couple of weeks or whatever. This kind of stuff was all kind of dreamt up and seems pretty plausible. Like if the technology actually works, but there's these sort of nuclear proliferation questions and a whole bunch
that
of
come
other
into perspective. Yeah.
Yeah.
And what is the most advanced breakthrough propulsion that you can imagine briefly?
That I can imagine? I mean, there's all kinds of crazy stuff out there, right? So there's this like, the EM drive stuff, which I think is not real. And then there's the other sort of in the realm of science fiction-y things. There's these like Alcubierre drive sort of relativistic ideas that are probably also not real, even though they have lots of fancy math behind them. But yeah, I think like the nuclear stuff is super real. Like the in particular, like the nuclear thermal rockets are cool, but like again are not like I feel like they're not as a big enough jump to make it worth biting off all the nuclear demons to go after. I almost feel I feel like if you're gonna like build a nuclear rocket and bite off all of the issues with that, like the Project Orion sort of idea seems like much more compelling from the prospect of like so it's something we could actually build if we wanted to. It has a bunch of baggage, but the prospects of if we had this, what could we do with it are really compelling, I think.
Going back to we went on a very 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 interesting and much needed tangent, which was very very good. Coming back to you, I'm very curious about how did your 300 plus backers react after Kicksat? The deployment of Kicksat. How did you feel? What was your experience?
I mean, to be honest, like I think so many years passed between like the initial Kickstarter thing and like it actually working on the second attempt in 2017. No, wait, when was this? This was 2018, 2019 when we actually did it. I think it was 2019. So the Kickstarter was in 2011. And because of, an initial like failure in 2015, the first try, and like all these bureaucratic crazy hurdles and getting bumped off of launches multiple times, it was 2019 when we actually got it to work.
Yeah.
So 8 years passed from the initial like Kickstarter thing to when it actually, was successful. I feel like, people moved on. Like
back when you were working on this project, you were working with Justin. And so how was the idea first conceived? Like how did you guys come up with that we wanted to solve this problem?
So, I mean, the Chipsat stuff has been around for a while. There are like ideas floating around since the 90s at least. And Mason kind of really latched onto this stuff, I think, early in his academic career and was a big proponent for it and talked about it a lot. And there was a NIAC, which is this NASA Innovative Advanced Concepts thing. So Mason got a NIAC award to work on Chipsats. I feel like, what was this? Maybe like 2007, 2008, something like this. And then there was Justin, who was a PhD student, whose thesis was on length scaling and spacecraft dynamics. So like this idea of like, how does everything scale down? If we did make something really small, like what would be possible? This kind of these very big picture, ideas. So I got involved as an undergraduate, I think in like 2008. And basically, I was a physics major, you mentioned, and I sort of initially came into this as one of the things Justin was looking at was plasma charging effects, and like, could we use these kind of things to actuate a satellite? Can we use like interactions with the ionosphere and the Earth's magnetic field and things like this? So I initially got involved in that and actually running experiments on that stuff because I like knew something about, or very little about, but like sort of had a background to think about some of the plasma physics stuff and ran some really fun plasma physics experiments in a vacuum chamber with a xenon ion thruster and all kinds of crazy things, and made glowing purple plasma, which was really fun. So we did some of that stuff. But basically, that was like this kind of, it was geared towards looking at, could we do this on a chipsat? At some point in there, we all kind of just were like, hey, like, we looked at this chipsat stuff. Justin was looking at it from like this more theoretical perspective, and I was doing hardware experiments in the lab. And we kind of, at some point, all thought it would be a good idea to like try to build a chipsat as like an exercise. So there was some early work. Cornell has this Center for Nanotechnology and has this big fab facility for building stuff like this. So there was another undergraduate student at the time who got trained up to work in there and started like actually building wafer scale things. And it was clear that was a really challenging path to go down and was going to take a lot of money and a lot of time that we kind of didn't have. And so then we kind of had this other idea of, let's try to just build something with cheap off-the-shelf parts and like see like how, if we just made a circuit board with, crappy solar calculator, solar cells, and like a microcontroller and whatever little, car key fob radio chip we can buy, like, let's just build something like that and see what we can do with it. So somewhere that idea popped out. And basically I was an undergrad kind of doing random hardware hacking and building stuff. And so like I basically got sort of somehow roped into doing that and like laid out the first PCB that like evolved into what we flew on Kicksat somewhere in that like 2009, maybe sort of 2008, 2009 timeframe with Justin. And so we built the first ones. They were like, hand soldered. First time I laid out a printed circuit board, didn't know what I was doing. Pretty terrible. There's pictures of these floating around. And sort of not too long after that, we got this random opportunity. I think Mason got a phone call from somebody to fly these on an ISS experiment that went out on the outside of the ISS. And it was one of these things where like someone backed out at the last minute and we had to get them there in 2 days for, this launch opportunity. Kind of crazy thing. And so we did. We put some boards together and they flew. And we, it was all last minute and we couldn't get any signals from them, unfortunately, but we did get them back a couple years later and they were basically fine and still worked and stuff. So this is kind of interesting. So it was like, yeah, maybe these cheap COTS parts are fine in low Earth orbit. So that was kind of fun. And yeah, basically like we did a bunch of stuff. Justin did a bunch of, this kind of theoretical stuff. And I ended up just like building things. So we ended up just building circuit boards and kind of figuring out, yeah, we can build something that's like 3 or 4 grams that kind of does everything we've been talking about. And, initially the original NIAC work and like this, it was a real chip that was like centimeter-ish scale and a gram or so. We're like, well, we can build something 3 times that size for like $20 and actually like try to go fly it. And like, so that's kind of what it evolved from this work, trying to actually build a chip into like, well, we can build printed circuit board things. And this was kind of, early days of like Arduino and, all that stuff. So these things were getting much easier to do. And there was stuff all over the place. It was, a couple years post iPhone and, Arduino was around. And so all this stuff was readily available. We could buy parts and like, there was a big maker community doing this kind of stuff. So it sort of became like extremely doable. Sorry, there's things ringing. So yeah, basically that's sort of how it happened. Initially, I think Mason's goal was to build a real chip, and then it kind of became clear that was going to be really tough and really expensive. But we could build something, not that far off for really low cost and quite easily. So we built some prototype boards, and then Justin graduated, and I kind of took over the project. As a PhD student, and we kind of, we got to a point where like, okay, yeah, we built these things, we did a couple of revisions and improved them and did a bunch of testing, and then we kind of were like, yeah, I think we would like to fly these in space, kind of thing. And this is also, Cubesats had kind of just recently kind of blown up in a major way, and NASA started this program called ELANA, Educational Launch of Nanosatellites, that awards free Cubesat launches to university teams. And so that happened, around this time as well. And so we kind of saw this opportunity to apply for a free Cubesat launch. We're like, yeah, maybe we can do this. Maybe we can sort of pack a whole bunch of these Chipsats inside a Cubesat sort of mothership and get one of these free Cubesat launches. The stuff's pretty cheap to build. So it all kind of seemed doable to, somewhere around 2011. It seemed like a reasonable thing to try like stuff a whole bunch of these things in a CubeSat and try to fly them. So we did. Basically, like I applied for one of these Alana launches. At the same time, I put it up on Kickstarter because I was a starving grad student. We had no funding for any of this stuff. So it was like, needed some money to build hardware. And then the rest is history. Basically, we got the Alana launch awarded and raised some money on Kickstarter to go build everything. And then from there, it kind of took on a life of its own. So like, I ended up going up to NASA Ames because someone there saw the Kickstarter and was like, hey, we do small sats at Ames. We've got this phone sat thing and a bunch of CubeSats going on here. You want to come hang out here for the summer? So I did that and then just stayed for 2 years. And most of the, the hardware work, definitely all the CubeSat stuff, and some of the Chipsat stuff as well happened at Ames. So I basically went out there for the summer, thought it was awesome, and there was a bunch of good stuff happening and access to, expertise and facilities to do all the stuff I needed to do. And it just made sense to just camp out there for the duration of the Kicksat thing. And a few people at Ames and at NASA headquarters thought it was really cool and were super supportive of it, and actually really went to bat for it because it ended up being super challenging on the sort of bureaucracy side in a bunch of ways, with people sort of concerned about debris and all this kind of stuff to actually get it to happen. So a lot of NASA folks really kind of went to bat for the project and helped us make things happen. So that's sort of how historically how it happened, was sort of this, like, I was an undergrad, Justin was a PhD student. We sort of initially tried to build a chip, and that turned out to be really hard. Then we tried building some printed circuit board stuff. That was pretty easy and really doable. So we built a few of those, and then Alana. It was the combination of Alana sort of came out, and there was a call. It was like the second or third Alana call that was released. So there's this opportunity to get a free CubeSat ride, and Kickstarter also had just kind of become a thing. And there was like a New York Times article about Kickstarter that I remember reading and then checking that out, and it seemed like, actually possible. So I basically threw both of those out there at the same time, and they both kind of worked.
What was your experience from this entire initial Kicksat project? Further on, you were able to transition, and how were you able to transition into the following missions, moving away from Kicksat?
Yeah, I guess in many ways, Kicksat sort of like set me up for, like, it sort of made my career in some sense, right? It like basically put me in front of a bunch of people. It basically got me, a bunch of connections within NASA and all this kind of stuff. So it really kind of put me in a position to then, go on and do other things with small sats and stuff like that. So since then, there was Kicksat 2, which was just follow on me being stubborn and enough people in NASA being willing to put up with me trying to do this again. And that ended up being harder than the first one from a regulatory perspective, because there were more people who heard about it and were clued in and decided they didn't like it. So it was harder to do it the second time. We got bumped off a couple launches and had to sort of wrestle with a lot of government red tape kind of stuff over like 5 years to try again. And thankfully it worked the second time. So I guess that, I've learned a whole bunch of things along those lines too. That are like, I think it's, so that a couple of Kicksat missions. I was also, when I was at Ames, I was involved in this project called PhoneSat, sort of on the side, which was really great, which was this, smartphone CubeSat thing that was originally a thing with Google in collaboration, where they used an Android phone as the guts of a CubeSat. So that was actually something, I worked on as well. And then it turned out Kicksat 1, the CubeSat, was actually a phone sat. It was a phone sat bus that we kind of like traded favors on. And so the guts of the bottom chunk of Kicksat that was the CubeSat that ran everything was a phone sat. And then Kicksat 2, we kind of went in a separate direction. So since then, basically Kicksat 2 thankfully successfully finally flew in 2019. Projects since then that we've gotten involved with, I mentioned this like Pocket Cube thing. So we tried doing one of those. Unfortunately, it doesn't look like it's really viable to do one of those in the US. I was kind of doing it half as a little experiment to see if we could get it to squeak through the FCC and stuff, and it hit a brick wall. So it seems unlikely. So we're probably not going to try that again. So that was sort of a dead end. We were actually going to try that magna torque or attitude control thing. And it was basically a situation where I had some cash to buy one of those Pocket Cube rides that I had to spend. So I was like, okay, let's give this a shot and see. And it was sort of a project where I roped a bunch of undergraduates in to like working on it as part of a capstone. So it was this opportunity that like I had, a chance to try it on the cheap and see if it could happen. So that we tried unsuccessfully. That may get resurrected at some point with some European help.
Well, there are quite a few companies that are doing that now. I mean,
yeah, they're all in Europe.
Yeah, Alba,
where it turns out you can fly.
Yeah, you've got a bunch of them that are working on this.
Yeah, so we may try this again, but try to like get a European university partner on board to actually like sort of fly it as a European mission instead of us in the US where we can't license it. So we'll see how that goes. And then the other one that's happened recently that's on orbit still, although the mission's kind of winding down, is a mission called VREX we did with NASA Ames, which was 3 1U Cubesats that had actually just LoRa radios, but they had UHF and S-band LoRa radios. And we did a bunch of mesh networking kind of demonstrations between the 3 satellites, so they all talk to each other. And then we used this feature of the newer S-band LoRa radios. They can do 2-way time of flight ranging. It turns out they can do like sort of meter level accuracy ranging between the radios. So we actually did this between the 3 CubeSats and tried to use this to do sort of relative navigation kind of things. Like, can we figure out where everybody is in relation to each other using these kind of LoRa radios? So we did that, and we had GPS receivers on there to try to get ground truth positions to see how good of a job we could do. So this was the most recent flight.
What's next for you? What's next on your research agenda? What are your current and next research projects?
Yeah, we're doing a bunch of stuff. So we have maybe an opportunity here sometime in the next year to fly 2 1U CubeSats. And we're going to probably there try to do, maybe try the Magnetorquer attitude thing again, and actually fly it. And this is super cool, actually, because it's valuable at this CubeSat scale as well. Basically, like, doing attitude control, even most 1U CubeSats don't do attitude control. It's like something that's really hard and really expensive. So we're trying to put together a few different things, I guess, but we're trying to put together a set of open source CubeSat avionics. And my inspiration for this has been sort of the PX4 Pixhawk drone stuff, if you're familiar with this. That's super popular and basically the de facto standard in the research community. It's an open source avionics, boards and open source software to run drones. So inspired by that, we're trying to do that for CubeSats. So we have a main sort of flight computer board that's all open source stuff that is actually what we flew on VREX, and it's evolved from what we flew on Kicksat 2. It's our stuff that we keep kind of improving and as we fly it multiple times, and it's been tested and flown. So we have these boards that we've open sourced, and we're also now working hard on software to go along with this, because in my experience, it turns out the software development effort on these kind of small satellites ends up being I don't know, it's sort of like an afterthought a lot of the time, and it's a huge issue. Like, often the software is written from scratch for each mission. It's being written by people who aren't embedded software developers. They're like aerospace or mechanical people who are sort of doing this as a necessity and are not necessarily very good at it. And it ends up taking a lot of time and effort and ends up being really error prone in my experience and like the source of a lot of issues. So we're trying to develop a good, well-tested software framework for CubeSats that's geared towards the kind of people who end up actually building these systems in academia, at least, who are mostly aerospace and mechanical people without embedded software expertise. So this project is called PyCubed. It's being led by one of my PhD students, Max Holliday, who's an awesome electrical engineer. And I have a bunch of undergrads hacking away at the software side of this summer to try to put together a real software framework for it. We kind of, the software side of it, I should mention, the reason and the source of the name PyCubed is that it actually runs Python natively. So this is getting at this idea of, people who aren't embedded software experts. So we're trying to put together, like a basic framework with all the stuff you need that's easily customizable and a nice set of APIs, all of which you can kind of script in Python so that you're not stuck, dealing with like memory management in C and like, register settings for microcontrollers and all that stuff. So like a basic sort of scheduler and set of drivers for all the hardware on our board and everything so that you can kind of get right to work and do stuff in nice high-level Python so that, these student project teams and things like this can not suffer in the ways that I have suffered on CubeSats with like hacky, Arduino stuff and C code spaghetti on microcontrollers. So that's one project. And yeah, hopefully if we get this right opportunity for these 2 CubeSats in the next year or so, we're going to fly that stuff. And part of that's going to be a polished ADCS implementation that's cheap and open source. So we've got kind of the classic magnetometer, gyro, sun sensor setup, but we've implemented a bunch of smart algorithms behind this. So we have like all this, all the calibration stuff that you need to actually do it right to calibrate on orbit, and so that you can actually achieve reasonable, say 5-ish degree pointing accuracy, and that coupled with the magnetorquer stuff that we talked about to actually do full 3-axis pointing. So this is the hardware to do. This is dirt cheap, right? It doesn't, and it's stuff you can build into the PCBs, so there's no need for extra hardware, motors, etc. And it's a clever software stuff that we're going to implement, and it's going to be part of the baseline Python packages that you can just use.
What are those hard problems that you're itching to tackle in the next 5, 10, 20 years time frame, and do they even exist yet?
So I guess on the small sat side of things, we have these attitude control sort of various ideas I've talked about. So there's also I have a general kind of passion for kind of open source, low cost, reduce barriers to entry for people to do space. There's Kicksat was kind of along those lines, at least aspirationally. So we're still interested in pushing those boundaries as much as possible. So this PyCube thing, we're trying to put this out there and make it really easy, and reduce, like, the cost is one thing, right? But there's also a ton of like expertise sort of barriers to entry too, especially the first time you do this. So we're trying to reduce those as much as possible, and like enable students and people at schools maybe that haven't flown a CubeSat before. It's still a small number of schools that have programs like this. So open it up to more places, people in more places at more schools. And then, on the technical side, solving some of these attitude control problems for small spacecraft, I think, is interesting to me. So like doing it super, super cheap on the magnetorquer end of things, and then doing it at the high precision, high performance end in much smaller packages to enable kind of astronomy applications is something we're working on. Hopefully we'll get funded, fingers crossed. There's a bunch of other crazy stuff that we could talk about that's sort of different flavors of space. So on the completely opposite end of the scale, I and a friend and collaborator, Jeff Lipton at University of Washington, just got funded for a NIAC to look at deploying very large space structures.
That's cool. Okay.
That are sort of using kind of crazy mechanical metamaterial ideas to have really high expansion ratios. So you could take something that's like, order 5 meters, on a side, fits in a Falcon 9 fairing, and then like expand it out to like a kilometer long, potentially. So there's that idea. I guess I'm super interested in, the point of that was to avoid robotic on-orbit assembly. But I think one of the biggest challenges right now that I'm super interested in, and a lot of people are working on in space, is kind of heading towards real robotic autonomy on a lot of these systems, and for a bunch of reasons. Right now, even our robotic spacecraft are super, sort of human in the loop, and very, not very autonomous. So I think generally making these things, more truly autonomous is of interest to me. And there's a whole bunch of really awesome problems. One of the current, hot areas is robotic on-orbit assembly, like trying to, anything that doesn't fit in a rocket fairing, either has to get folded up and sort of unfolded in some kind of crazy origami-like scheme, which is really difficult to do, or you have to launch the raw materials and assemble it on orbit. And I think that problem of how do you actually enable robots to autonomously build even simple like a truss structure that's very regular and things like this is really hard, and a bunch of people are interested in this right now. There's also these sort of like autonomous robotic servicing, like refueling kind of ideas to refuel existing satellites. So I think a bunch of this like robotic autonomy stuff is sort of an area that I'm really interested in as well, and trying to figure out how to do that kind of stuff without a human in the driver's seat.
So you've had a breadth of opportunity to develop and contribute into futuristic technologies. And in your viewpoint, at what point does science fiction become science fact?
I don't know. Like when we build it and it's real and it's actually out there, that's obviously the final thing. But there's always this really fun interplay, particularly with space technology, between science fiction and what we go do. And it's been true since the beginning, right? Science fiction. I mean, it's interesting that the science fiction was only about 50 years ahead of the real thing.
Yeah.
Kind of pretty much for the whole space, the whole realm of space travel and aerospace engineering. And I almost feel like I feel like the real thing, I feel like engineers kind of caught up to the science fiction authors in a lot of ways, and that science fiction has been lagging recently in recent decades to some degree. But yeah, I mean, I don't know. Yeah, I think there's a really healthy interchange there and interplay that historically that I like to see continue with particularly with hard science fiction with people who have engineering backgrounds who are technically literate writing science fiction and kind of pushing us all in various ways to do big things, and I think it's always good.
And that kind of brings it home. And our question that we ask each of our guests is, why space, and why space now?
I mean, I'm kind of with Tori Bruno on this. I don't think we have a good reason to do it. I think it's just that it's this fundamental human need that we want to explore. We want to kind of go out there and find things that we haven't seen before and figure out how things work and why they work. It's sort of this just deep-seated thing that makes us human. I don't think there's a better reason than that.
Well, Zach, it's been a pleasure. What a fruitful conversation, and we've been around the entire universe, I would say. And so thank you. Really appreciate you coming on here and talking to us about such a complex and unwavering topic.
Yeah, thanks, guys. Thanks for having me. It was fun. And now I have a new podcast to listen to. I didn't know about you guys before. So great. Yeah, thanks so much.
There you go. Cheers. Well, thanks for joining us for another episode of Space Forward. Stay tuned for more deep dives, explorations, and journeys we have in store for you. Follow us on Spotify, subscribe on Apple Podcasts, and on YouTube, or hear you next time. Don't forget to send us your comments and questions, and we will feature them in our next episodes.